Now, before we look at the details of the algorithm which is going to discover frequent item sets in our market basket data, we have to first look at how the data itself is represented or implemented or stored on the disk. So if you recall, I mentioned that the total amount of data that will be gathered across all the transactions and all the stores would be maybe around the order of terabytes. So if the data is around the order of terabytes, it clearly cannot fit into the main memory of a machine. For that reason, we have to imagine this data as being stored on disk. Moreover, we are going to assume that the data is stored in a file on disk. So we are not talking about data stored in a database system here. We are rather talking about data being stored as a flat file on the disk. And the contents of the flat file are as follows. So here you see a file of transactions. The first transaction is also called basket 1, and the items that were part of the transaction are stored one after the other. So there are 5 items in this basket, and those 5 items are represented by a list of 5 item IDs. So we are going to assume that our items are represented as IDs which are positive integers, and that is because if items are represented as positive integers, then each item can take up about 4 bytes of space. In contrast, if you were to represent items as strings, then each character in the string would require 1 byte, and there will obviously be many items whose names are significantly longer than 4 characters. So representing items as strings is going to require more space for storing a single basket. So it's more efficient to represent items as positive integers so that we know that each item is going to take up 4 bytes of space. Now at the end of the list corresponding to basket 1, we can have some kind of a delimiter, which could be another integer with the value of -1. Since our items are positive integers, no item will have an ID of -1, and so -1 can be set aside as a special delimiter demarcating the boundaries between one basket and the next basket. So when we see a -1, we know that the current basket is terminating there, and then we can look at the next 4 bytes to look at what item marks the beginning of the next basket. And we'll continue reading a sequence of 4 bytes until we again encounter a sequence of 4 bytes which corresponds to the representation of the integer -1, and that in turn will terminate the next basket, and so on. So this is how the file containing all the transactions is going to be organized on the disk. So the organization of the file on disk is basket by basket, as we just saw in the figure. So if all this data is stored on disk, clearly we'll need to read that data from the disk into main memory while we run the algorithm that will discover frequent item sets for us. So when we read in the file or a small section of the file into the main memory buffer while parsing the file, we are going to look at the transactions basket by basket. And when we are looking at a particular basket, we can always look at all pairs of items in that basket. We can generate all pairs of items in the basket if we have a list of all the items in the basket. And if we can generate pairs, then we can also generate triples, that is, groups of three items that are drawn from the basket. So if there are n items in a basket, there will be n choose 2 pairs of items and n choose 3 triples of items in a particular basket. So we are going to assume that expanding a basket into pairs, triples, and so on is not going to require much time, because this is an operation that is being done in main memory. And when data is operating in main memory, when you're operating on data in main memory, your speed can be much faster than the speed of doing IO, than the speed of transferring that data from the disk into main memory or from the main memory back to disk. So we are going to assume that we can in general expand a basket of items into all possible subsets of size k. There will be n choose k such subsets. We can generate all n choose k such subsets by using k nested loops to generate them. So for example, when k is equal to 2, how do we generate all pairs of items in a basket? Well, we have one variable that will iterate from 1 to n, and another variable that will iterate from, well, we could make this also iterate from 1 to n, and then we look at item I comma j in the loop. So we have a double loop, I varying from 1 to n, j varying from 1 to n, and we look at we look at the ith item and pair it with the jth item. But obviously this will involve a lot of repetition, because not only will uh, for example, not only will the second item and the fourth item be grouped together into pair, but again, so when I is equal to 2 and j is equal to 4, the second item in the basket and the fourth item are being grouped into a pair. But when I is equal to 4 and j is equal to 2, again the fourth item and the second item will be grouped into a pair. So there will be duplication. So in order to avoid duplication, and also if we independently allow I and j to vary, it's possible that we could be grouping together item number 2 with item number 2. So this obviously is not a valid pair. We want both the items in a pair to be distinct. So in order to avoid this kind of repetition and to avoid grouping together the same item in the pair, we can make j vary from I plus 1 to n. So when I is equal to 1, j will vary from 2 to n. When I is equal to 2, j will vary from 3 to n, and so on, until when I is equal to n minus 1, j will vary from n to n. So by doing this, we ensure that all pairs among these n choose 2 pairs are generated, and no pair is generated twice. So there's no repetition in this for loop. And you can imagine extending this to k nested loops in order to generate all sets of size k. Now we are assuming that generation of all sets of size k, since it is being done in main memory, can be done pretty fast. So the main bottleneck for us is going to be the IO from disk. It's not going to be the processing in main memory. As long as the main memory is large enough to fit the relevant data that we are operating on, we are going to assume that the processing power of main memory is not going to be the dominant factor in determining the time complexity of this algorithm. I still have to explain what the algorithm is, but when I explain it, you have to keep in mind that the way we are going to ascertain the time complexity of the algorithm is basically based on how much of disk IO we do. It's not going to be based on how much of processing we are doing in main memory. So the true cost of mining disk resident data is going to be the number of disk IOs, not the processing in main memory. And this is very similar to what we discussed earlier when we looked at index construction. Recall that we discussed in detail the external sorting algorithm when your data does not fit into main memory and has to be stored on disk. How do we sort a list of items which is stored on disk? So again, there we assume that the main bottleneck for us is going to be the amount of time that disk IO is going to take, and we try to minimize that time. So in practice, the algorithm that we are going to use for generating association rules or finding frequent item sets is going to read the data in passes. So as we discussed, the whole of the data is going to be stored as a file on the disk, and we may have to do multiple passes through this data, and in each pass we are reading the data in all the baskets. And obviously we can't bring this entire data into main memory at the same time. We will just be reading this file bit by bit. So we'll first bring in the first few baskets into main memory, process them, then we'll bring the next few baskets into that same chunk of main memory, overwriting what we had earlier, because we've already processed the earlier baskets. So we can use that same space in main memory, that same buffer space, in order to store the next set of baskets, and we process them, and then we bring the next set of baskets into main memory, and so on. So at any time we are only storing a fraction of this file in main memory. So when we do a single pass through this file, each basket would have at some stage been brought into main memory and processed. And the total cost of the algorithm is going to be measured by how many such passes we make through this file. That will determine the overall time complexity of the algorithm.